I know he's done these presentations for us. And when I saw the flyer from the last one he did, I thought, this guy, he looks good. We're going to have Shad do this one. So one of the things we briefly discussed 2 weeks ago was our assembly of the radioisotope thermoelectric generators for NASA. And I'm going to let Shad just talk about it because that is what he does. And it's very cool stuff. So they're all yours.
All right, thank you, Don. And I actually did meet you when I first started here. I went on one of the site bus tours that you were in charge of. But so that's been almost 10 years ago, so it's been a while. But good afternoon, everyone. I want to thank you all for taking time out of your day. I know everyone's busy with school and work if you're participating from a work environment. So thank you for taking time out of your day to participate in this presentation. I'm always amazed and quite truthfully honored and grateful for those that are interested in this program, and for everyone that that is seeking to go down this field of whether it's space exploration or the topic I'm going to be discussing. And so I'm honored and grateful to be able to talk to the people about our program and the role we play in space exploration missions. I'd also like to thank Anne and Don for putting this on, and the University of Wyoming for giving me the opportunity to give a glimpse into what it is that we do out here on the Idaho desert. As Don mentioned, my name is Shad Davis. I graduated from Idaho State University with a bachelor's degree in mechanical engineering in 2002, which to me, it seems like ages ago. I actually started my career working at Los Alamos National Laboratory. That was my first job working in this very same program. And Los Alamos is responsible for manufacturing and producing the plutonium-238 oxide fuel clads that go into our radioisotope thermoelectric generators. So I got to see that part of it for 5 years down in Los Alamos. And then for the past 10 years, I've been working for this program here in Idaho on the receiving end and kind of the end of the program, as far as being able to take the fuel clads, assembling them into the generator and testing them, the generators, and ultimately delivering them to the launch site. For those of you that have never been around government work, there's a lot of acronyms, and a lot of those I'm going to throw out to you, and I apologize. It's just kind of our nomenclature around here. When I refer to an RTG, it's called a radioisotope thermoelectric generator, and that's kind of the terminology we use interchangeably with radioisotope power systems, which is the name of our program. When I stop and think about it, I'm always amazed at the role this program has played in such a grand and exciting space mission. It's a mission that has had and continues to have a profound effect on research, science, and engineering across the world. When I really think about all the people that are involved in bringing a mission together, it spans the entire world, from universities, research industries, commercial industries, and the various government laboratories across the world. Is pretty amazing. To think back, the first public demonstration of an RTG was in 1959, and it was demonstrated in front of President Eisenhower at that time. And here we are over 60 years later, and RTGs are still needed, are still being sought after for providing power for space missions. And when I look back at my career and think back to that first engineering class I had back in 1998, I never would have imagined when I walked into that engineering class that I would be where I am now, working for this program and playing a small part in a space program that's really, quite honestly, one of the most amazing things that I've ever been a part of. So thank you again for joining in this talk, and I surely hope that this is as interesting to you listening as it is for me to give it. Let's see if I can get the slides to move. So just kind of an overview of what our program is made up of. As I mentioned, there's a variety of Department of Energy laboratories that make up this program, as well as partners with industry and university. As I mentioned, I worked at Los Alamos National Laboratory, where we were responsible for producing the fuel clads made out of plutonium-238. Oak Ridge National Laboratory, that's located in Oak Ridge, Tennessee, they're responsible for manufacturing and producing the iridium hardware, which is a metal alloy that is used to encapsulate the plutonium-238 oxide fuel. So Oak Ridge produces and fabricates that hardware and then delivers it to Los Alamos, where Los Alamos takes the plutonium-238 oxide fuel pellets that they've processed and fabricated, and then encase them in this iridium cladding and weld them together. And that makes up the fuel clad. That fuel clad is then shipped up to us now here in Idaho, where we take those fuel clads and assemble them and put them into the generator, and then subsequently expose the generator to a series of tests to make sure that it's flight ready. Some of our other industry partners are spread throughout the country. We have universities that do a lot of research and life type testing for us on the generators themselves. We have commercial entities that actually are responsible for kind of the design and fabrication of the radioisotope thermal generator itself. They do a lot of research and development work in that area. And so really there's a lot of people involved to bring one of these radioisotope thermal electric generators to fruition. It's pretty amazing. This is a great graphic. I love showing this to folks. It really gives a great visual representation of our history of the program. In fact, this year will mark our 60th anniversary of the very first launch of a radioisotope power system. That particular RTG was launched aboard a Navy satellite in what was called the transit program at the time. That was in 1961, and it produced just under 3 watts of electrical power for that particular satellite. Originally, it was developed as just a supplementary power source because that satellite relied heavily on batteries at the time to produce the power. And so this was a kind of a trial run of providing nuclear power in concert with the use of a battery. So throughout the 60s and 70s, missions with RTGs were pretty consistent, with the transit program in full swing through the 60s. Then we had the Apollo program that bridged kind of the 60s into the 70s that utilized RTGs as well. And then we went on to exploring the outer planets in the 70s with the Pioneer missions that performed the first flyby of Jupiter. We had the Vikings 1 and 2 Mars landers that had RTGs on those particular spacecraft and missions. And then the Voyager 1 and 2 flyby missions that kind of culminated the end of the 70s era that reached clear out to the planets of Saturn, Uranus, and Neptune. And those Voyager spacecraft are actually still sending signals back through our deep space network, through NASA's deep space network. And then into the 80s, we had the horrible tragedy of the Challenger accident that really kind of put a kibosh on a lot of NASA's mission launches through the 80s, until eventually they were able to launch the Galileo mission in 1989 that had an RTG on it. And then subsequent to that, into the 90s and 2000s, we had the Ulysses and the Cassini mission launches and the Mars Pathfinder missions of the 90s. And then the 2000s, we had the Pluto New Horizons mission that was the first first mission spacecraft to take up close pictures of Pluto, and that occurred in 2015. It was pretty amazing. It was launched in 2016 or 2006, excuse me, and it took that long to eventually get to Pluto. And then our missions culminated with just the Mars Perseverance rover landing on Mars here just last month. And we have a lot of missions that are upcoming, and hopefully this mission, the use of RTGs will continue on into the future. To kind of take a step back into our history, these are the last 3 generations of RTGs, starting with the very first one. You can see that image up there, cutaway view up in the upper left-hand corner. This is what's called the Systems for Nuclear Auxiliary Power RTG. This was the one that was developed and used in the Navy Transit Satellite Program. And then also supported some of the Apollo missions. You can see astronaut Alan Bean there on Apollo 12 deploying the actual heat source containing the plutonium oxide and getting ready to assemble it into the RTG itself. This particular RTG kind of evolved through the 60s. The initial RTG, as I mentioned, produced just under 3 watts of electric power only, contained about 100 grams of plutonium oxide, or actually it was plutonium metal at that time. And then through the 60s, eventually got up to the SNAP 27 version, which was able to output about 60 watts of electrical power for the Apollo program. The next generation of RTG was what was called a multi-100 watt RTG. This RTG was almost 2.5 times the amount of electrical power as the last version of the SNAP RTG. Most notably, these generators were used to power the 2 Voyager missions. Each Voyager mission contained 3 of these mounted to it. And as I mentioned, was able to output about 160 watts of electrical power each. Kind of interesting, just last year, actually, NASA was able to reestablish contact with Voyager 2. There was some downtime involving the Deep Space Network, and so they were able to reestablish that communication. And so that kind of gave proof that the multi-100 watt RTGs are still providing the power needed to send signals back from these spacecraft. And there's still a few handful of electrical or scientific instruments that are still being powered. NASA anticipates the power of the RTG to essentially disintegrate to 0 by around 2025. But to really think about it, that's nearly 50 years of power producing that these particular versions of generators were able to produce. The kind of the behemoth of our RTG is what's called the general purpose heat source RTG, shown here in the bottom left. This was able to put out about 300 watts of electrical power, so it was double that of the multi-100 watt RTG. These particular RTGs were used on 4 missions: the Galileo, Ulysses, the Cassini, and the Pluto New Horizons mission. The Cassini mission just ended in 2017 with the intentional descent of the spacecraft into the Saturn atmosphere. And then the Pluto New Horizons mission, which is still ongoing, and the mission life was actually extended through 2021, is the only current one that operates off of one of these GPHS RTGs. So one, you might want to ask yourselves, or I ask myself all the time, why do we even need nuclear power in space? You know, my history background is mechanical engineering. I took one nuclear engineering class in college, so I never would have thought my whole career would have been around nuclear. But you know, the more and more I work in this industry, the more and more I see and recognize the benefits of nuclear power, and that goes with being able to provide power up in space. You know, there's a lot of missions out there that utilized solar for producing energy, and those missions were highly successful. So you might ask, well, why not always use solar? And this graph is kind of a good technical justification as to why solar isn't always the answer for missions. As you can see, and it's intuitive to know that the further you get away from the sun, the less energy you're able to harness from the sun. You know, it requires bigger and bigger solar panels as you get further and further away from the sun to produce the power needed. And so that's where nuclear power becomes much more appealing as exploration further and further away from the sun comes about. One of the downsides with nuclear powered missions is it usually comes with a heavier price tag for the mission, and can have schedule impacts just on the sake that it is a nuclear device that we're launching into space. And so there's just some inherent additional requirements that can have schedule impacts on a particular mission. But really, you know, for a device that is static, that has no moving parts, it produces reliable, usable, constant power. So it's very appealing in the sense that it's not dependent upon the sun to provide that power for a particular mission. In the instance of Mars exploration, there's been, you know, four successful Mars rovers that have utilized solar panel for the power, but unfortunately they're limited to certain regions of Mars for exploration, typically around the equatorial area, to be able to harness the most power from the sun. So with the last Perseverance rover and the Curiosity rover that are up there now, it really opened up the gamut to be able to explore Mars in a much wider range, because we don't have to rely on the sun for producing power, you know. And so we have a constant, consistent power source that is not affected by the atmosphere of Mars, dust storms. You know, that dust has a dramatic effect on solar panel efficiency. And so nuclear power is very attractive in that regards, especially for Mars types missions. As I mentioned, there's no moving parts, so there's no maintenance involved with these particular heat sources. There is some advancement and research going on with dynamic type nuclear power systems today. And ultimately those would require moving parts within the RTG, but kind of a trade-off with that is they suspect that they would get more efficient with these dynamic systems, but more to come on those in the future. Our current version or current generation of RTG is what we call a multi-mission RTG, or MMRTG. There's one of those acronyms for short. This particular device can produce up to 110 watts of electric power at beginning of mission. It's not a very big generator. It's only about 2 feet tall, 2 feet in diameter with the fins there, and weighs around a little less than 100 pounds with the fuel inside. It contains about 11 pounds of plutonium oxide fuel. It's only about 6 to 7% efficient. Some of the waste heat that is utilized is actually captured and utilized elsewhere to warm spacecraft instruments, for instance. So there is ways to harness some of that waste heat that the generator gives off. This particular generator uses the same heat source configuration that the general purpose heat source RTG used back for the Pluto New Horizons mission. You can see up here in this graphic shows kind of an exploded view of what that general purpose heat source module looks like. It's very intricate components made up of a variety of graphitic type materials. This module itself is about a 2 by 2 by 4 inch brick, or block, I should say. It contains, each one of these blocks contains 4 fuel clads inside of it. And then there's 8 of these blocks that are stacked up to power the MMRTG. There's 8 of those modules inside the MMRTG. A lot of interesting history with the general purpose heat source modules themselves. They're intricately designed. Every component has a specific function in regards to primarily the safety of how this, the safety of how these modules would react to an insult on, say, a launch accident or on the launch pad, or say a launch accident should the spacecraft re-enter the atmosphere. These general purpose heat source modules have gone through extensive safety testing, modeling and analyses, as well as the fuel clads themselves, to ensure with utmost confidence that the module itself would survive any kind of accident, insult, and not release any plutonium oxide fuel into the atmosphere. So there's a lot of time and money spent on this little guy here that provides the heat for our RTG. Here's some images down here. This is actual kind of a rendition of a fuel clad. This is the iridium cladding that surrounds this plutonium oxide fuel pellet that's shown here. How do we get power from our plutonium-238? I want to start off by saying I'm by no means an expert when it comes to thermal electrics or even semiconducting material. I understand the basic principles of what's going on and how this functions. So I'll try to do my best to describe what's going on with our particular generator. So the principle here is based on what's known as the Seebeck effect. And I'm sure there's some of you tuning in that probably know this much better than I do. It operates on this principle of having 2 dissimilar metals joined together and providing a temperature difference across that metal to induce a electrical potential. And when you wire these what they're called thermocouples together, you can now get energy or current flow from the device. And so that's the principle that an RTG operates on. So you can see in this image, here's kind of an electrical or kind of a schematic of what's going on here. We have our heat source, which is provided by our stack of general purpose heat source modules here. Surrounding the modules is 768 thermocouples, and they're kind of arranged in bricks and modules surrounding the general purpose heat source stack. And each one of these thermocouples are configured in 2 series and parallel wiring chains, and that's done intentionally so that any one of the failures of these thermocouples does not result in dramatic power loss of the generator itself. And so there's a lot of engineering and science going behind how that's all wired together. And so you have the heat that's provided from our general purpose heat source modules, that's heat's radiated to a hot junction where we have our semiconducting materials that are joined on each end by a hot shoe and a cold shoe. The cold side is kind of the atmosphere of the generator, may it be space or an atmosphere of a planet. So we have a temperature difference that's induced across these thermocouples. And as I mentioned, they're all wired together in a circuit, and we're able to produce that electrical current out of the generator and into the spacecraft to provide the power needed. It's kind of fascinating to know that the hot junction, the heat that's produced by our general purpose heat source, is on the order of 950 degrees Fahrenheit. So these modules get very, very hot. The cold side of this thermoelectric circuitry is on the order of 200 to 400 degrees Fahrenheit. And so we got a temperature gradient across that semiconducting material. That temperature gradient is directly proportional to the amount of current that flows out from our generator. And really there's one right here is an electrical connector, and that's where all the power and instrumentation comes out of that one connector of the RTG. So there's one cable that comes out and is supplied to the spacecraft, or the rover in this instance. For those of you that want to really dig into the kind of the thermoelectrics and material side of this, there's a lot of research, a lot of fascinating papers that have been written about semiconducting materials that are used, especially throughout the history of this program, and advances into looking at other materials to try to increase that heat transfer efficiency, to increase the electrical conductivity while maintaining the thermal conductivity low. So there's a lot of good research out there that I just, if you're interested, to go out there and Google that and read as much as you'd like on all that information. Our program, the life cycle of it, as I mentioned earlier, there's several DOE Department of Energy labs that are involved in this whole life cycle of the program. And it starts with plutonium-238 production. It's quite amazing to think this is a recent capability that we've just reestablished in this country. In the past, we were relying on legacy plutonium oxide and also receiving plutonium oxide from another country to provide for this program. But we're now starting to produce it in our own country, and it starts with a nuclear process of irradiating neptunium targets, and from that neptunium bombarded material, we're able to harness out the plutonium-238 oxide from the neptunium nuclear reaction that's going on there. That plutonium oxide is actually produced. The neptunium targeting is done at our two reactors in this country. One is at Oak Ridge and one here in Idaho National Laboratory. From there, the plutonium oxide gets shipped, as I've already mentioned, to Los Alamos, where the raw plutonium oxide is processed and then pressed into these plutonium oxide pellets. There's an image there of an actual pellet. And then the metal alloy hardware is fabricated and manufactured at Oak Ridge, and then that gets shipped to Los Alamos, where they encapsulate the fuel pellet and weld that clad to make a fuel clad. The fuel clads are then shipped up to us here in Idaho, where we assemble those fuel clads into the general purpose heat source graphitic components that I showed you earlier. And then we ultimately fuel and test the thermoelectric generator to ensure it's ready for flight. Once it's been flight certified, we package that generator up into a shipping container and ship it down to Kennedy Space Center for this last mission in particular for launch. So that's kind of a quick summary of the whole life cycle of our program. And then as far as the actual workflow specific to INL, this is the kind of the bread and butter of what we do here at Idaho. And it starts with the fuel receipt of those fuel clads from Los Alamos. They're shipped to us in shipping casks. We take those casks, open them up, cut open some inner containers to retrieve the fuel clads inside of them. We take those fuel clads and introduce them into what we call our module assembly glove box. And this glove box is a term for a containment box that we're able to control the atmosphere of that environment from the perspective of moisture and oxygen. It's important we keep those contents of moisture and oxygen low so that there's no detrimental effects on the graphitic components of the general purpose heat source. And so we have an environmental control system as part of this glove box that's important in our process. So we take the fuel clads and assemble them into the general purpose heat source modules. These are very specific components. They're all serialized. There's a lot of quality control that goes behind this whole process. We ensure that certain fuel clads are arranged in certain modules, and then the stack is all predetermined so that we maximize the thermal output of the fuel clads and ensure that we maintain or are able to obtain the right amount of plutonium oxide fuel in these general purpose heat source. So all of that is predetermined, pre-calculated, and pre-selected, and it's a very rigorous process. We do a series of inspections and measurements of the general purpose heat source once it's fueled. At some point in this process, our generator arrives at our facility, and the configuration this particular generator is in, it's flight ready in the sense that it's only an electrically heated unit. So our industry partners have gone and tested this from an electrical standpoint using an electrically heated unit to simulate the nuclear fuel that we're about ready to put inside of it. So it comes to us, and we perform a series of electrical checks and visual inspections of the electrically heated unit to ensure that there's been no damage done during shipment and that it's ready to be fueled. So here's just some images of that process that the electrically heated unit undergoes. Now that the electrical unit has arrived, our general purpose heat source modules are assembled. We're ready to merge those two together. And this is our most intense operation, I would have to say. It's very time consuming. This process takes on the order of 6 to 8 weeks to conduct. Essentially, it's the process that's most intense from an operations standpoint. We have highly skilled operators that work through gloves in the glove box and remote manipulators using specialized tooling to do this assembly and fueling process. There's just some images here. That, again, this is done in a controlled environment from the standpoint of moisture and oxygen content. This is the first time that the generator is now being powered by nuclear material. This is the first time we hook up our electrical monitoring equipment once it's nuclear fueled to begin monitoring the power and the voltage and the heat that the generator is outputting through the instrumentation. And so here's some images of our electrical team monitoring. As what's really important is we're lowering the stack, as you can see in this image. These general purpose heat source modules, as I mentioned, put off a tremendous amount of heat. And so we control that descent of the stack and are monitoring it with our equipment to assure we don't induce a thermal shock to the thermoelectrics inside the generator. It's very important that we don't exceed a certain temperature ramp as we're lowering that stack down inside the cavity of the generator. And so this is a very stressful time for our engineers and our operators, but it's quite exhilarating once we've lowered that stack and we're actually starting to produce power from our nuclear material. Once that assembly is complete, we're on to our acceptance testing. The first test we do is a vibration test. So the MMRTG is subjected to a variety of vibration levels to verify that the generator will survive conditions experienced during launch. That's kind of the objective here, is to ensure that it's able to sustain launch and also Mars entry events. So our test objectives are to ensure that power output remains unchanged as a result of the vibration tests, and that no components are displaced or damaged, that we don't destroy the fins that are on there, that they don't shake loose, or other components are damaged based on the vibration levels that we're subjecting it to. And the third objective is to ensure that the internal thermoelectric power circuit is not damaged or displaced, and that we're still able to maintain electrical isolation from the thermoelectrics inside, that we haven't created a short as a result of our vibration tests. And so this is another one of those tests that is probably the most likely that we're going to damage the RTG at this point. But the test is very controlled to certain test levels that, as I mentioned, would be subjected during the launch. And so this last mission, everything operated as expected. This test went off with flying colors as far as the expected outcome of the RTG. The second test is our mass properties test. This is kind of a straightforward, as the name implies. We're essentially determining the overall mass of the fuel generator. And also we're able to put it onto some instrumentation that is shown here, oriented in different configurations to determine the center of gravity of the generator. From there, we're able to calculate the mass moment of inertia of the generator as it's in its fueled configuration. It's important that these values are determined to meet certain specifications. It's the knowledge of the mass properties of the MMRTG contribute to the overall understanding of the mass properties of the entire spacecraft. It's a significant information in order to determine flight dynamics during its trip to Mars and to assess the fuel needs, for instance, of the flight corrections it does on its way to Mars, as well as how the spacecraft will respond during entry, descent, and landing maneuvers. So the information we gain from doing this test of the MMRTG all gets kind of rolled up into the overall understanding of the rover itself and how it interfaces and interacts dynamically with the spacecraft. Our third test is a magnetics test. Because this is producing electrical current, it induces an electromagnetic charge on it. Excuse me. And so we have these magnetometers, and they're essentially devices that measure the magnetism of the generator as it's producing the power. And so we position these magnetometers very strategically within this room here to measure the entire profile of the electromagnetic field that the MMRTG is giving off. And we're essentially determining what that magnetic field is to ensure that it's below a certain level to meet specifications. This information is kind of important to understand how the magnetic field of the MMRTG might affect, say, instrumentation that's mounted near the MMRTG on the rover, and to understand that it's not, to understand that magnetic field to know that it won't affect any kind of instrumentation is important for the mission folks. Our last test is the thermal vacuum test. The whole purpose of this test is to subject the RTG to space-like environments. So we insert the MMRTG into our thermal vacuum chamber and perform a power test. We pull a low pressure, low temperature environment on the RTG to essentially get to the point where the only radiative, or the only heat transfer, is radiative, to simulate what this MMRTG would see on its mission. And once we've achieved those low pressure, low temperature conditions within the thermal vacuum chamber, we are able to measure the power output to determine, what kind of power we can get from the RTG under these types of conditions. This is our last test, and essentially at that point, once it's passed all those tests, it's deemed flight ready. And so we follow that up with packaging the MMRTG into a shipping cask and loading it onto our trailer to ship down to Kennedy Space Center. Each one of these test stations is led by a test engineer. We have very knowledgeable and experienced test engineers that follow the MMRTG to the various test stations, and then they're responsible for leading these various tests. And then each test station has highly skilled and trained operators that support that operation. A lot of training going on, a lot of training involved. We were training and practicing this for 2 years prior to actually receiving the flight unit to fuel. So by the time we got to the point of actually doing this work on an MMRTG fueled, it was kind of second nature to us, because we'd practiced and trained for so many evolutions and so many years prior to this. So it didn't really have any issues throughout the test of the last MMRTG, as we expected that would not occur. So we assembled a team to travel down to Florida to perform what we call our launch integration operations. And for this last mission, this occurred in March, April timeframe of last year. We shipped a team of INL engineers and operators and other support personnel down to Florida to support the launch integration activities. Here's some images of us offload of, this is our transport trailer that we hauled the RTG down to Florida in, and then here's some operators disassembling our shipping cask. And then we performed some follow-on electrical checks to make sure that we didn't damage the RTG during shipment. This particular facility is really, it's down in Kennedy Space Center, and it's really designated for our use. It's kind of our building specific for RTG handling operations. There's a lot of upfront work that goes on in order to be able to do work down in Florida, to be able to do nuclear work down in Florida. More importantly, we have experts perform some safety hazard analysis to ensure that any of our operations done down there would not damage the MMRTG to such a degree that we could have a release of nuclear material. And so there's a lot of evaluation, studies, and analysis that go in prior to us even arriving down there in Florida for us to be able to do these types of operations using nuclear powered devices. So about 3 months prior to launch, we do what is called a hot fit check. That's kind of a term that's floated around there and used over the history. Jet Propulsion Laboratory was actually responsible for the mission, and so we interfaced directly with them to provide the power source for, specifically in this instance, the hot fit check. This is essentially the first time the nuclear powered generator is mated up to the rover. That image there in the center is the actual image of them getting ready to mate up mechanically the MMRTG to the rover. This is done at a facility called the Payload Hazardous Servicing Facility down in Kennedy Space Center. So this is we're down there to support the mechanical and electrical integration. So they made up the rover mechanically, electrically, and then eventually turn over all power to the rover from the RTG. And so this is, like I mentioned, the first time that nuclear power is being provided to the rover. And so JPL goes on to perform a series of functional tests, diagnostics tests of the rover to ensure that the power from the MMRTG is as expected. There's just a couple of other images of those operations going on. This actually occurred prior to the hot fit check, in which we assisted the Jet Propulsion Laboratory in mounting the spacecraft adapter. This is the interface fixture between the MMRTG and the rover. Then about 9 days prior to launch, we perform our last integration activities. We actually deliver the MMRTG to what's called the Vertical Integration Facility at Cape Canaveral Air Force Station. This is the facility where the Atlas V rocket has been assembled, and all the components are staged and ready for us to deliver the MMRTG. The Mars Perseverance rover is already assembled up into its aeroshell and cruise stage and is sitting atop the rocket in the payload fairing. And so the last piece of the puzzle is us delivering the MMRTG to perform the final integration activities. And essentially, it's a kind of a repeat of what we did prior to this over here in the Payload Hazardous Servicing Facility. We're essentially doing the final mechanical and electrical mating of the MMRTG. For me personally, I was kind of in charge of leading this activity. This was by far the most stressful operation I was involved in to see this, to see our MMRTG being hoisted. That was about 170, 180 feet in the air. This huge crane lifting our MMRTG up. I don't think I breathed. I don't think I took a breath. It didn't seem like, anyways. I was just sitting there watching that being hoisted up there, just hoping and praying that nothing would go wrong. Prior to this, actually a year prior to this, we went through a dry run of this operation, and everything that we do is meticulously done. All the equipment is certified and inspected and checked to absolutely assure us that nothing would go wrong. However, you can't help but have those bad situations cross your mind, and of course it did at that moment for me. Because just this is one major piece of the component or piece of the mission that if it failed, they would essentially have to scrub the mission. So that wasn't lost on me in understanding the importance of this particular activity. But once we got that MMRTG landed up on that platform, it was pretty a huge relief for me. Here's just the next couple slides, just show some really cool images of some of the Jet Propulsion Laboratory and United Launch Alliance operations. Kind of neat to see the rover being assembled to its descent stage and then packaged up in the aeroshell with the cruise stage mounted on top. Here's a cool picture of the Ingenuity helicopter that they're hopefully going to deploy here in the next couple of weeks on the surface of Mars. The United Launch Alliance is responsible for everything associated with the rocket itself, the Atlas V rocket. Here's some images of just various operations they did to assemble the rocket. The upper stage Centaur being hoisted up to the top of the main engine. Here you can see the payload fairing, which has the Mars rover inside of it. This is all getting hoisted up and assembled. And then we show up with the MMRTG to do the final mating and integration. Mission went off on July 30th successfully. As many of you perhaps watched some of the video of this launch, you can go on the United Launch Alliance website and see some really up close, cool videos of the launch if you get an opportunity to check that out. And then about 7 months later and 300 million miles traveled, the Mars rover is lowered to the Mars surface. Really neat. For those of you that haven't seen any of the videos or the images, I just happened to throw a couple of them in here that really kind of were interesting to me. This was an image taken from the HiRISE spacecraft of this is the aeroshell with the parachute deployed. And then if you go on to, if there's a QR code here, if you feel like you want to inclined to scan that, that'll take you to this really neat NASA simulation, all the way from the cruise stage deployment throughout the entry into the atmosphere. And it's kind of a 3D, you can manipulate the spacecraft and rotate it around, and as it's descending down into Mars. It has a lot of neat data as far as altitude and speed in various stages as it's entering the atmosphere. So I encourage you to go onto NASA's website if you haven't done that already. This image here is the actual crane maneuver operation of the rover being lowered down to the Mars surface. This image here is the first image taken by the Perseverance rover from the HazCam once it was set down on the Mars surface of Mars. I am going to show, for those of you that have not, perhaps weren't following any of this mission, this was some video captured from cameras mounted on the various components. It's about a 3-minute video, so I hope you enjoy this, and I hope it works on your end.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applicant indicates chute deployed.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Both yes, valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here on Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Hopefully that video came through for those on the participating in this. If you don't, if you didn't come through, there's a video link down there. I just encourage you to pull that video up. It's really quite amazing to actually see something from another planet and all the intricacies that went into successfully landing that rover on the Mars surface. Just a quick slide here, kind of giving us up-to-date activities of what's occurred since its touchdown. We actually receive information back from Jet Propulsion Laboratory to kind of keep us up to date and let us know that our power system is delivering the optimal power and the nominal power levels. And so we get those power curves distributed to us to know that the MMRTG is functioning. So that's always kind of cool to still be involved in the mission, and from that standpoint. Some of the other things that have occurred, they did their first maneuvers of the rover, did some kind of a test of the wheels out and such, and completed all their health checks of the Perseverance rover, captured the first panoramic view from the Perseverance rover as well. They have actually taken some wind readings. Pretty amazing. Another part of this was they recorded sound, both captured the wind on Mars, as well as the first laser operations they did with the with the SuperCam, as they actually were able to capture the audio of the laser striking the rock. So pretty cool to listen to if you get a chance to log in and check that out. And then upcoming is the actual first flight of the Ingenuity helicopter that's on the underside of the rover. So that they'll be deploying that, I believe, first or second week of April. With that, just to kind of sum up, here's some, for those of social media buffs out there, here's some social media platforms that you can follow, both the INL as well as the various missions and the rovers that are out there from NASA. There's some websites there that have all kinds of mission information, up-to-date information on current missions going on out there. And then also I wanted to kind of throw up there the internship career opportunities here at INL. There's some websites there that you can visit for those of you that are interested in employment opportunities or internship opportunities here at the laboratory. There's a specific one called the Center for Space Nuclear Research that is more kind of applicable to our program. Its central focus is in the field of research and development of advanced space nuclear systems, including power systems. There's research in nuclear thermal propulsion, and also, of course, the radioisotope thermoelectric generators. So I just encourage you to go onto those websites and see what's out there. Also, I want to throw a plug out there for the American Nuclear Society. They host a conference. It's called the Nuclear Emergency Technology for Space Conference. it's really a place where all of these companies and laboratories come together, really focused on nuclear applications in space. It's really talks about the latest and conceptual future technologies in this field of both nuclear thermal propulsion and fission power systems, as well as the thermoelectric conversion technologies and dynamic systems that are being researched now, is really the focus of this conference. So I encourage you, if you ever have the opportunity to participate in that conference, to go. I've gone to a couple of them, and I believe there's one for 2021 occurring at Oak Ridge National Laboratory next month. With that, I'll open it up to any questions that anyone has.
No question?
And
No
silence.
questions. I bored everyone to sleep.
I do have one question here for you.
Okay, go ahead.
So how does like the size, weight, and like the amount of power contribute to like the space missions? Like, do you have to ever like configure a different like MMRTG for like different size of like space like components or anything like that?
So my understanding, it really comes down to kind of the power needs of a particular mission. Unfortunately, right now we only have one version of a power source, so it's kind of that's all we can provide really from a Department of Energy standpoint. And so missions know that, they know what the MMRTG is capable of. And so really it kind of comes down to designing the mission and science instruments and power needs around what we can provide. Now, obviously we can provide multiple of these generators for any particular mission. So those power values and numbers are very well known, as well as like the degradation of the RTG. So that kind of data is well known, and that all gets provided to a mission to know whether this particular MMRTG is acceptable for use to supply the power needs. I don't know if that answered your question. As far as like any other properties, that's all information that's we actually have a user's guide written for the MMRTG that provides all the engineering and science and data for your generator.
So yeah, it does. Thank you.
There are future missions that are looking at using, in fact, possibly exploring ideas of a dynamic system, as I mentioned earlier, that would be a different configuration, different size, because it uses less fuel, but it uses a dynamic system. So there's some other auxiliary power conversion technology that goes with a dynamic system. So that's stuff that's being looked into as well.
Other questions? I myself thought it was really interesting in the sense that it's just hard for me to imagine how you're even testing all of this when you're doing it without having space right there, you know, just great.
Yeah, we do our best to, obviously, like it's, you know, you can't mimic every situation that space has. We do, the tests are really kind of centered around trying to achieve, you know, like launch type conditions are very well characterized, very well known. So those types of tests we're able to replicate. As far as the atmosphere, that can kind of get tricky at times because you can't always simulate, obviously can't simulate no gravity conditions for our testing in our thermal vacuum chamber, but we can definitely test to low atmosphere as far as pressures and temperatures. There's other considerations that go into play as far as, you know, even the heat side of things. And so our testing tries to do the best that it can to ensure that the MMRTG is going to produce in those types of environments. In fact, there's some other, if I could just kind of show some backup slides, here's some missions that are kind of on the horizon Johns Hopkins University, their applied physics laboratory is looking, has the Dragonfly mission coming up in the next few years. They're looking at sending basically kind of a aircraft or a helicopter or to the to the moon, to Titan, which is a moon of Saturn. And so they're looking at using MMRTGs for power for that particular spacecraft. And that planned launch was 2026. I believe it's still, it might have been pushed out a year. Another possible mission coming up is, and it's still in the down select phase, is the Trident mission, looking at doing a flyby of Neptune's moon Triton. That's a nuclear powered mission, and it's competing with 2 other missions that are using solar panel. And so that down select process is supposed to happen sometime this summer, I believe. And so I'm always biased to RTG power. So I'm hoping that the down select chooses the Trident mission, because that'll give us another opportunity to provide a power source for a NASA mission. So those are some of the things coming up on the horizon for us.
Exciting though.
Absolutely. Yeah, it's a great time to be in this program for sure. Although I have to admit that the 80s and the 70s and 60s were by far probably more exciting because of all the development that was going on and, the consistent missions that were being launched. Unfortunately, we're kind of in this, cost conservative mode with these missions are getting more and more expensive. And so there's more and more time between missions. But this is exciting to see the potential for definitely one mission coming up with Dragonfly and potentially a second one with the Trident. So we might have a busy 2020s.
Any final questions that anybody wants to ask Shad? Okay, well,
I might mention, if you do think of any, Ann and Tyler can get a hold of me and I can track Shad down anytime.
Absolutely. And I can pass them on to the people that could probably answer them.
It's all I'm doing.
well, I have right at noon, and just to let people know, our next presentation, we're looking at April 7th, and probably at 11 o'clock as well. And Dawn is organizing a speaker. And so just stay tuned and we'll bring up the next one, some promotion on it in the near future. Other than that, those that have been on, thank you so much. But Shad, thank you so much for this information. It's just very, very fascinating. And as there's a couple of comments in the chat area about super interesting. Thank you so much. And thanks for the presentation. It was fascinating.
Absolutely. And I'll just put one more plug in. We're looking for the next generation of engineers and scientists on this project. And so I really encourage those of you out there interested in this field to look at the avenues. Not, Idaho is not the only place that is part of this program, but there's a lot of an older generation of this program that has a lot of experience and knowledge, and we're looking to pass that on to the next young engineers and scientists that come aboard. So, and thank you again for this opportunity. I truly enjoyed it, and I'm honored to talk to folks and to spread the word about our program.
Thank you very much. We really appreciate it, and take care.